All right, so I think we should slowly get started. Well, thank you for everyone coming. So we have our Wednesday seminar today with George Constantinides as our distinguished speaker. So I think I know you since my days as a PhD student. I was kind of like anything that I associated with hardware design at Imperial or in the UK was typically George. So it was really, really kind of interesting to follow his all the research he's been doing. And so now, meanwhile, I also became a professor. So George is here. He'll talk today to us about his recent work on hardware datapath and machine learning. I have some interesting details about him. So he's a professor of digital computing, and he's the director of the Imperial Early Career Research Institute, which what I just learned, about 5,000 PhD students.
Yeah, so it's the entire Imperial College PhD and postdoc program. 5,000 PhD students, 2,500 postdocs. Yeah, roughly speaking.
So I think after
not that I have to read that many PhD theses. Yeah.
Right. So I think after he was, I guess, head of associate dean of engineering, he needed a challenge. So he took up that challenge. He obviously served as technical PC chair at FPGA, FPL, FPT. So quite important hardware conferences. Published over 200 papers, meanwhile. And I learned you enjoy family and espresso. So we have a quite good coffee place here in the department. I'm not sure if it matches, but quite experienced and Australian-trained coffee staff. But I don't want to get into the way of this presentation. So George, thank you for being here. And I'm excited to hear your talk. Thank you.
Thanks very much, Tobias. And thank you for the invitation. Thanks to everyone for coming. I was reflecting on the fact I was last giving the Wednesday seminar, I think about 15 years ago, so some time ago, when I was actually on sabbatical leave here. And it's great to be back in the building. Not that I have been a complete stranger to the building ever since. So I'm going to be talking about a couple of pieces of work. I asked Tobias, what would you like me to talk about? And here are the two pieces of work that I'm kind of most excited about at the moment. And he said, yeah, both. So you get two talks for the price of one. So I'm going to do two shorter talks with a short pause in the middle, take any questions from the first of these, and then maybe we can go back to it at the end if there's time and you have additional questions. So the first part of the talk is going to be on Boolean logic and deep neural networks, bridging the gap between these two worlds. And this is joint work with my PhD students, Marta Andronic, Erwei Wang, and with my collaborators, Peter Chung and James Davis. It's also joint across the Imperial and AMD collaborations. And then secondly, I'm going to talk a little bit about E-graphs or equality saturation, if you prefer, for Datapath design. And this is joint work with my PhD student, Sam Coward, who's actually just graduated. I would strongly recommend hiring him for anyone who's looking for either a postdoc or indeed a lectureship candidate. And Theo Drain at Intel. So, part one, Boolean logic and deep neural networks. Okay, so back in 2019, I was thinking about my world of hardware and the kind of newly accelerating world of deep learning. And I published a position paper called Rethinking Arithmetic for Deep Neural Networks. And this is a figure taken from that paper. And I think it kind of shows where I'm coming from in this piece of work. So I thought I'd talk through it a little bit. So the bottom left is a kind of really tiny, obviously, toy deep neural network. You can imagine that this tiny toy deep neural network, each node in here is operating on real data types, and it's computing a dot product followed by some kind of nonlinear computation, as you would expect to find in a modern deep neural network. So that's one view of what a deep neural network looks like. Now, if I, as a hardware designer, want to come along and create a really high performance, high throughput accelerator for that tiny deep neural network, perhaps the most obvious hardware accelerator design that I could come up with, there are many, but perhaps the most obvious hardware accelerator design I could come up with is literally to create a circuit following the same topology as the graph in the bottom left, to stamp that circuit, that deep neural network in that topology as a circuit. Now, the first thing I have to do, of course, if I'm going to do that, is I need to decide what data types I wish to operate on. So let me make an arbitrary choice in this particular case. I'm going to choose 4-bit fixed point data types. And then, once I've defined that, I can actually code that in your favorite hardware description language, let's say in Verilog, and compile that into whatever the underlying technology is. So let's just say 2-input Boolean gates. And if I do that, then this other graph, the big graph here, is actually what I get. So that graph is also a representation of a deep neural network once it's been implemented, but the nodes there are Boolean gates, either 1-input or 2-input Boolean gates. So there's a few kind of commonalities and differences here. So, I mean, one really obvious difference is that's got a lot more nodes. That doesn't have many nodes. No big surprises, obviously. Another difference is the lack of structure, apparently, in that large graph. But there is some structure, and I've tried to indicate that with color here, in that there are clusters that are more tightly interconnected, and that's because they belong actually to arithmetic units within the data path. So a single multiplier, for example, tends to be quite highly connected between 2-input logic gates. So putting those differences aside, there is kind of one fundamental thing that's staring at us from this picture, which is that they're both directed acyclic graphs that operate on some data types. Right? And I think that's the fundamental starting point for this piece of work, is like how can we bridge this world where we're really thinking about directed graphs operating on data types, whether they happen to be Booleans or whether they happen to be real valued word level data types. Okay, so there's a few different ways that we then started to peel this onion, and we certainly haven't got all the way to the core of the onion. The first one is a paper that came out at the same year in 2019 called LUTNet, Lookup Table Network. So for those of you who are familiar with FPGA technology, which is one of my specialities, FPGA is the kind of the core of the soft logic inside an FPGA is the Boolean lookup table. And so we asked the question, well, how can we actually expose what it's possible to encode in a Boolean lookup table in a way that we can learn that in a standard deep neural network training framework? The basic idea here was that if you look at things like binarized deep neural networks, which were all the rage in 2019 in hardware-efficient networks, then multiplication becomes XNOR operation, so it's a really cheap Boolean operation. And so what you actually end up with if you map that into the hardware is you end up with Boolean lookup tables being used for very specific, very particular operations. And so one thing you could do is to look at it from an architecture perspective and say, well, how can I make my FPGA architecture better suited to those particular operations? And that's some things that my colleagues, for example, in the University of Toronto have been doing a really good job at. I took the opposite view and said, well, how can I make use of the flexibility of the underlying Boolean lookup tables in the implementation? Okay, so this was our first cut at this idea. We basically said, well, let's replace those XNOR gates, those Boolean multipliers. Let's replace those with arbitrary p-input lookup tables. So we're going to refer to p-LUTs as physical lookup tables here. Well, the first thing we need to do if we want to use that and play with that in a modern deep learning setting is we need to have differentiable lookup tables. So how do we have differentiable lookup tables? Well, one way, by far not the only way, and I'll talk about follow-on work in a moment, but one way is to lift the Boolean space to a continuous space, to derive an interpolating polynomial through so that it exactly agrees with the Boolean function on the particular points that are defined by that Boolean function, and then we have a continuous function that we can then throw into our favorite deep learning framework and get some useful results. And that's essentially what we did in this work. So, I mean, it worked really well, actually. So we ended up with about half the area that you needed to by just mapping a deep neural network into the FPGA naively, for the same accuracy, obviously. So, but there are some limitations here. I mean, for a start, if you're working with, in this case, it's k-input lookup tables, then the number of trainable parameters scales exponentially with k. Which is not surprising because there are k-input lookup table, there are k entries in the 2 to the k entries in the k-input lookup table. So you would expect the number of trainable parameters to scale exponentially with k. The other thing is that it contains, this design on the left contains what I would call exposed data paths. So what I mean by that is that you've got these physical lookup tables, you then add them together, the outputs, and you do your standard kind of batch normalization quantized activation function. You then have a quantized output, y0 here, and it would be nice if that whole thing was inside a lookup table, right? Because then you don't have the, you've got quantized inputs and quantized outputs. You don't have to worry about quantization issues in the middle. So, so those are the kind of, I guess, two limitations of that very first initial piece of work we did there. Interestingly, a year later, Xilinx, as was, AMD as now is, were thinking along, I would say, complementary lines. So they decided to publish something that they called logic nets. The reference is down here at the bottom. And logic nets produced a design that looks like this. So now they have put that entire thing inside a lookup table. But it's no longer a physically sized lookup table. It's just a virtual lookup table, which ends up being coded in Verilog as a big case statement and then gets mapped into physical lookup tables. So they've put the entire thing inside there, which is nice. But what is the thing that they've put inside there? It's just a standard dot product followed by batch norm and quantized activation. So this is a kind of straightforward implementation of a standard component that you would see in a deep neural network, but then actually implemented as a big case statement in Verilog. So what that means is that it's easy in this case to think about, they support in their work multi-bit words at the inputs and outputs. There's this idea of a logical lookup table that gets mapped into physical lookup tables, so we don't have this limitation. It ends up learning a continuous piecewise linear function rather than, which is what any deep neural network that uses rectified linear units as its activation will learn. So it learns a continuous piecewise linear function rather than the more general Boolean functions that we had in LUTNet. One thing that's really nice about this is that there is no weight quantization. Right? These are arbitrarily precise real arithmetic weights, because the only quantization that happens is at the input and the output of a lookup table. So the computation that's happening inside can be evaluated arbitrarily precisely, and then you just enumerate what the possible input values are and express that down in your case statement. So there is no quantization of weights here at all. Okay. So that's quite nice. So, I mean, the obvious thing then for us to do was to take the work we'd done with LUTNet, where we had more general functions, and to merge it with the idea of logic nets that puts the summation, the batch norm, the quantization, activation inside. The trouble is that the number of inputs here can be very large, and you still have this situation where you have to enumerate all the possibilities of the inputs to this Boolean function. So, the first thing we've kind of taken two approaches to this. So the first one we call polyLUT. So now we're getting much more up to date. So this is a couple of years ago. My PhD student Marta and I published this work called polyLUT, where we essentially replace what's inside the logic net's logical lookup table with this much more complex richer set of features, where you essentially can have arbitrary monomials up to a certain degree which you can tune. So if you turn that degree down to 1, you're back to your linear functions, you're back to logic nets. If you turn that all the way up, you get more and more rich class of functions. Now, on the basis of that doesn't look kind of that interesting if you were just going to map that into a data path that looked like this picture. But remember, this whole thing is enclosed inside a Boolean lookup table. So from the perspective of looking at the two bits of Verilog, they look the same. I mean, obviously the elements of the truth table values are different, but they're the same size truth tables, the same topology, connectivity, and so on. Those extra multipliers that you see there are not real multipliers. They're hidden inside the Boolean lookup tables, and therefore essentially come, if not for free, for almost free. And so you can get this richer class of functions that you can implement at a very, very low cost. So, that was the first thing that we've done, and you can actually go and that's open source. You can go and play with that, and it's got quite a few people using it now. The other thing that we did was to say, well, what other class of functions do we know that allow me to arbitrarily closely approximate continuous functions? I mean, we know polynomials, right? So there they are. I mean, there's another class of functions that's kind of popular at the moment, and that's those that are implemented by deep neural networks, right? So what we said was, well, what about if we just hide a small neural network inside one of these Boolean lookup tables? So here, we published this paper here just last year, polyLUT, NeuroLUT, I shouldn't say polyLUT there, NeuroLUT, hiding neural network density in Boolean synthesizable functions, where essentially what you can do is you can hide one of these kind of more sophisticated functions inside this logical lookup table. Again, it's essentially for free, because the only thing we're doing is enumerating the inputs to identify the outputs. And so you get this kind of thing for free. The nice thing here is that this computation, we can make this internal neural networks, if you like, arbitrarily dense and arbitrarily deep, subject to the usual things around training. And so you can hide that. And so essentially what you end up with is that you end up with training a deep neural network that's just a normal deep neural network, but with a specialized sparsity pattern that happens to correspond to efficient hardware implementation. So that's a nice way of thinking about it, I think. So again, this is open source. You can go and play with it. So both of those two approaches, polylut and neuralut, are probably best accessible via Marta's GitHub there. The tool flow looks like this. We have a training framework built on PyTorch. This one here is the illustrating polylut, but there's equivalent for neuralut. That will train your deep neural network. It will then automatically convert that into an LLUT by enumeration, generate the RTL, perform synthesis, place and route, and you end up with a hardware implementation. So let's kind of just give you some idea about what this richer class of functions buys you. Let's look at that with a really kind of toy network. So this is just a two-layer network on a toy data set of a couple of spirals, and we're trying to separate blue from red in these data points. So this is a tiny network, and therefore we don't expect it to have very good properties in terms of being able to separate these two data points. And indeed, if the functions that are being implemented by these nodes are just linear functions, that is indeed the case. This is the kind of, after we've trained for a while, this is the best kind of separation that we can get, which isn't really much separation at all between these two spirals. The other two show the kind of results that we get for the two examples of more richer function classes that I spoke about. And essentially, remember, these are essentially for free in the hardware. So this is the polynomial case, and this is where we're hiding the neural network inside the Boolean lookup table. And so, unsurprisingly, in the neuralut case, you get the same kind of decision boundaries that you would expect to see. You get kind of more pieces, essentially, in your piecewise linear function that allows you to more neatly separate them. In the polynomial, again, if you think about it, unsurprisingly, you should expect kind of curved decision boundaries because these are implementing polynomial functions. We do, however, come up against some instabilities in the training process here. And again, those of you who have worked in polynomials probably not very surprised by numerical instabilities in this. So essentially, we get kind of very nice, smooth decision boundaries when it works. This one's very reliable because essentially all the existing deep neural network training techniques and meta-heuristics and so on are built upon networks that kind of use those kind of decision boundaries. So, is it useful? Well, it is if you want really low latency, and that's really the target application area that we're interested in. So here we are looking at applying this in the context of ultra low latency inference that you might need, for example, in CERN when you're doing particle physics experiments and you want to classify, is this an experiment outcome that we want to store, or is it an experiment outcome that we want to throw away? There are obviously other low latency use cases, I'm sure you can imagine. So on the left there, you can see a trade-off between the test error rate of a network for one of these CERN test cases against the inference latency of that network using traditional versus using neuralut networks. And the reason there are a number of points in this is that essentially we can tune the size, the depth of the neural network in both cases. But for a given depth, the benefit is about 1.5 fold in terms of latency of the inference process. And then the right-hand side is just showing that doesn't actually cost you much. In fact, it gains you a little bit in terms of area once you take into account the trade-off between test error rate and area. Okay, so that was the first of my 2 mini talks. I'll pause there and take any questions on that, if there are any.
That's a good moment that we can try our question setup. Are there any questions so far?
Just a fairly naive one.
Just because it's recorded.
Just a naive one in the fact in the very first slide you said, here's my regular 6-node neural net, and over here's my natty bit of coloured stuff with clusters. Why had the symmetry of the first 6 nodes disappeared? Or is it just was it there but being hidden by the drawing mechanism?
Yeah, so by the symmetry we mean that essentially this one here is structured and this one here is not, right? Yeah, okay. So there's a couple of things going on here, right? So the first one is that inside each of these nodes are a number of different computational units, right? Multipliers, adders, other kind of operators, and so on. And so you can imagine this is a kind of hierarchical graph that hidden underneath are these other things. So you will get kind of a less obviously structured graph once you expand to the lower level of the hierarchy. But the other thing that's going on is that this is then being passed through logic synthesis process. And so then, at the point where you pass it through the logic synthesis process, all bets are off in terms of structure, right? Because it's heuristically trying to explore an area-efficient implementation in terms of those basic Boolean logic gates. Yeah.
So in a sense, if there's any shape or sparsity, like there's 1 somewhere in the matrix and 0 somewhere else, and then
that will be taken. Yeah.
In the spiral graph example that you showed us, how many bits are we talking about in terms of the number of inputs and number of outputs?
How many what, sorry?
How many bits of input are you handling?
Ooh, that's a good question, actually, and I don't know the answer off the top of my head. I'll have to get back to you.
Do you have a ballpark?
So I would guess it's probably 4, but that is genuinely a guess, and it will be written in this paper. So that's the place to look. But if you have any difficulty finding it, then I'll get back to you for sure.
Thank you.
Yeah.
Similar topic on this. There is sort of an optimal number of bits input per each actual LUT you're going to stamp out for something like neural LUT or poly LUT, right? So if I take a neural network that I want to run on these, do I have to train it with that topology in mind, saying, I'm going to calculate the weights for this exact configuration? Or can I take a trained network and then produce efficient weights for your poly LUT or neural LUT inputs and outputs?
Yeah, that's a great question. So we've worked on the basis that you are training from scratch, okay? But work in progress is not training from scratch. So I think there's also a kind of related question, actually, which is that there's a deeper, and this is one of the points that I go into in my position paper here, is that there's a deeper question, which is the correlation between an optimal network architecture and the data types on which it operates. those two are not independent. And it's something that I kind of poke at a little bit here, but it's not something that I've bottomed out by any means. Would love to. Anyone interested in doing a PhD?
All right, I think maybe a last question, and then if there's one.
So when you say you train and then you have these tables,
Yeah.
you don't need to cover every single bit pattern on the left, right? Because you're not going to have all of the values there. So say you're training this with 4 bits and you realize that you only use half of the values. That means you now need half of the area, right? So if you do things like dropout and ReLU, whatever, you start getting lots of zeros and start getting like sparse matrices in there.
Right.
And then you don't need to cover those sparse matrices. You end up with a much smaller set.
Right.
Do you do that kind of thing?
Yes, and the paper that describes that will be published in 2 weeks' time at FPGA. So that's not in the results here. The results here are not taking that into account. But essentially what we do is we use exactly the process that you just described to recognize when Boolean values here can be don't care conditions. And then we use those don't care conditions and we actually observe that I suspect it's essentially an application of Occam's razor that you get actually better generalization results by making use of those don't care conditions. So, yeah. Great. Let's move on to part 2 then. So just to say, I think it would also be wonderful to link up part 1 and part 2 of this talk by some wonderful paper that combines the 2 ideas. It's a rich area. Again, really happy to collaborate on this with anyone. But at the moment, we haven't done so. So I'm going to talk here about, not least because they're kind of sponsored by 2 different companies. So here we're going to be talking about e-graphs for Datapath. Okay, so the starting motivation here was looking at some of the manual hardware design that goes into floating point Datapath. And you might think, well, that's a done deal, right? People did that in the 90s and, don't have to think about that anymore. But actually there are teams, including the team that I did this work with in Intel, who do this for their daily work. And there are a number of reasons for this. But the first one is, yes, of course I can pick up existing libraries of floating point hardware IP and just instantiate them and stamp them out in my hardware design. That's really good because it simplifies my design process, but it also limits the exploration of what's possible if we know something about the operations that we're doing. Maybe we know something about limited ranges of the operands or something else that we might know about the context of what we're doing. So it limits the exploration, which leads to power, performance, and area being suboptimal. And of course, that's key for industry. And so what we end up seeing is that in reality, often bespoke floating point components are handcrafted to a particular task, especially in graphics processors. We see that a lot. So let's think about what a kind of modern floating point subtractor looks like. So this has been what a modern floating point subtractor looks like pretty much since the mid-90s. Before that, it wasn't as fast. So this is quite a significant innovation. I think it's 94, 93 that this paper was published, which it's called a near-far path adder. And so a near-far path adder makes up most of what a modern floating point adder looks like. So just to give you some insight into what that does, it's a recognition of the fact that if I'm subtracting 2 floating point numbers, then I can split this into 2 cases. And you can see there's a case split here because there's a multiplexer here. The 2 cases are the exponents are very similar, or the exponents are quite dissimilar. Those are the 2 cases. And the reason these cases are significant and interesting is that if the exponents are really close to each other, then the alignment of the significans of the mantisses of these two words is a very trivial task to complete. It's like no shift or shift by 1 bit. But on the other hand, that's exactly the case. So that's this near align box up there. On the other hand, that's exactly the case where after you do a subtraction, you may need to renormalize your numbers significantly because you might get significant cancellation. And that's why this near renorm is a big box, because that's a lot of work. On the other hand, you might have your numbers that are quite far away in terms of exponent. If they're quite far away, that means I need to shift them by a greater degree. So that's why I've got a big far align box. But on the other hand, that's exactly the case under which I don't have a lot of work to do in terms of renormalizing my floating point numbers at the end step, which is why it's a small box there. And so the clever bit here in this design is to recognize the fact that these two cases, the two big boxes, never occur simultaneously. Right? I never need to do both a significantly costly alignment and a significantly costly renormalization. And so by doing this case split between these two cases, I end up with a faster latency in my arithmetic unit. Okay, so that's a nice kind of thing that exists. What about if I think about the opposite question, rather than what's a really efficient implementation, what about if I think about what's a really easy to write implementation of a floating point subtractor? Probably looks something like this, right? I do my exponent difference, I sort them, I align them, I do a subtraction, I renormalize. Which would be nice to be able to write. Okay. It's really inefficient, though, when it actually gets implemented. Poor area, poor performance, and the fundamental reason is there that the components are bigger. You can see that's a 42-bit component in the middle. But it's easy to write, and it's easy to verify. This one, on the other hand, hard to write, hard to verify, but when you pass it through industry standard synthesis tools like Design Compiler, you get smaller and faster designs. So the kind of starting point for this work was, well, can we automate such transformations, and can we generate RTL that looks like this from RTL that looks like this on the left? Okay. And can we verify automatically that RTL that's generated? So around the time we were starting to think about this, thankfully, the University of Washington came out with a really nice library called EGG, which stands for eGraphs Good. EGG is an open source implementation of equality saturation or reasoning with eGraphs. And eGraphs, for those who are unfamiliar, allow for a very compact representation of equivalence relations, or in our case, equivalent designs in the implementation. And what kind of sets them aside is, so this is about kind of making use of rewriting. So here's an example of a rewrite there you can see that's going on. But we never lose the left-hand side of this rewrite when we apply the rewrite in an eGraph. All we do is add nodes to the representation. So we still had the left-hand side, we haven't lost it, but we also have the right-hand side. So here's an example. This you can just imagine this as being a direct implementation of A left shifted by 2, right shifted by 3. But if you look a bit more closely, you can see that the edges are from nodes that represent operations to these dotted nodes here. Those dotted nodes are classes, equivalence classes of expressions. Okay. And so that becomes, the distinction obviously is not there in this left-hand side, but it becomes more important, more interesting as we apply more rewrites. So let's say, for example, we apply the rewrite A left shifted by 2, right shifted by 3, can be rewritten as A right shifted by 3 minus 2. Then what will happen is we've introduced this new minus with 3 on the left and 2 on the right. And then we've introduced this right-hand shift here. And the equivalence class now encloses both of these to say that these are two equivalent expressions. and then there's another rewrite that's happening here, and we get a similar kind of development growth of the E graph. And so you can see that with a compact structure, I can represent many different equivalences in this case. And so we looked at how we can apply this to datapath design, and in a paper that was published at the Computer Arithmetic Symposium a few years ago, where essentially we came up with a big table, which I'll show you next but won't go through, a big table of different rewrites that were representative of the kind of things that the Intel design team we were working with did. And those were parameterized by bit width and signage. So there's a big table. Shows you the kind of rewrites that we extracted, that we captured. On the right-hand side, you can see an interesting column there that's showing sufficient conditions. So these are some conditions that need to be checked in order to be able to apply this rewrite. And you can see that, for example, while naively we can think, oh yeah, we're operating in integers, so therefore we know that we've got associativity of multiplication, for example. That's not true, because we're actually operating in finite precision bit vectors. So we need to be very careful to know under what conditions we can apply these rewrites, which is what the right-hand table is all about. So we extracted this bunch of things by looking at how the designers were working in the industrial group we were working with. So that, of course, raises the question, well, so is that it, right? Is that what these people are doing all day? Is that their job? Is datapath optimization just RTL rewriting? Just RTL rewriting? Well, it's a bit more than that. And the reason is what I said right at the beginning, that we're really interested in the context in order to produce things that are optimized for the context, designs that are optimized for the context in which they work. And so that actually corresponds to conditional rewrites. So we might have rewrites actually of the form, if some predicate phi holds, then I can rewrite the left-hand side as the right-hand side. So a kind of trivial example here is, if x is non-zero, then I can rewrite x over x as 1. So how can we identify those as we operate? So what we do is we attach value ranges to each class, to each equivalence class, so that we can analyze those ranges and understand when we can fire a rule. And we propagate those ranges via a form of interval arithmetic. Now, people who've worked with interval arithmetic may know interval arithmetic is a particularly weak form of analysis. Okay? So just for those of you who haven't worked with interval arithmetic, just to give you some insight into this, right? So if I say that x is the interval minus 1 to 1, then a naive application of interval arithmetic will tell you, when you're trying to find out what the range for x minus x is, it will tell you, well, it's minus 2 to 2, because the left-hand side is between minus 1 and 1, and the right-hand side of the subtraction is between minus 1 and 1. So in the worst case, I've got minus 1 take away 1 on the negative side, and 1 take away minus 1 on the positive side, okay? Which is, of course, true, but also hideously bloated in terms of the size of the range that we have there. So it's a very weak analysis. So isn't that causing us problems? Well, this is one of the really interesting insights from this piece of work, is that actually we can strengthen that analysis considerably through the use of these rewrites. And so just to give you again an insight into how that works in this case, one of the rewrites that we're likely to have is something of the form x minus x can be rewritten as 0. So we're no longer looking at the analysis of the expression x minus x in isolation. We're looking now at the analysis of the equivalence class that contains both x minus x and 0. Now 0 is, of course, the trivial interval from 0 to 0. And therefore, we get this intersection behavior when we're analyzing the E-classes, where we're actually interested in the kind of best analysis that we can get from all the different expressions that are grouped together in an equivalence class. So that's really nice, and it gives rise to this kind of virtuous circle, I would say, where you've got where you could grow the E-graph through the firing of some rewrite rules. That then allows you to refine the analysis because you get these extra intersections that you can compute. The analysis then, the refined analysis, allows you to fire more of these predicates, phi. The predicates allowing you to fire more phi's that you can show to be true allow you to fire more rewrite rules. More rewrite rules grows the E-graph, and so on. And so this is a really nice property that we explored a little bit in this paper here. And so putting that all together then, what we end up with is this automatic constraint-aware datapath optimization tool where you input RTL, builds an E-graph, goes around this rewriting constraint propagation and value range analysis loops, and then we do an extraction for minimum delay. It says here, but it could also be area or power or whatever. We've looked at a number of possibilities, and then you get out optimized register transfer level implementation. We've also got a path for formal verification, which I don't really have time to talk about right now. So just to give you some kind of insight into what that does, so on the left-hand side is a slightly more sophisticated example of the same kind of naive implementation of a floating point subtractor. Pop that through our tool, and it churns away for a while, and it pops out this thing over to the right, which says, hey, I've found this nice implementation, and it's got a near path, and it's got a far path. So we were quite pleased that you could rediscover this kind of well-known optimization in floating point arithmetic. Okay, so I'll kind of finish with some ideas for future work and collaboration that kind of cross both of these talks. So firstly, on the Boolean logic and deep neural networks, I'm really interested in exploring some deeper theoretical insights into the promising classes of function in the lookup tables and the network architectures, and that really goes back to the question I was asked earlier. And this data type architecture interaction, that is a neural network architecture interaction, again, going back to the question I was asked earlier. Secondly, for the E-graphs for Datapath, so I gave you that really nice picture. We've only really explored this for interval abstract domains. I'm quite interested in the kind of what works well, what doesn't work well, and why, and it's not really something that we've bottomed out in any depth. And again, I'd be really interested in looking at that. So I'll again mention that I'm open to collaborations, and I'm also recruiting for PhDs. Please, let me know if you're interested. And that's where I'll finish for now. Take any other questions.
Excellent. So first of all, let's thank George for these amazing presentations. This was really, really nice. We definitely have time for questions, so let me know. You have a question?
Yeah.
Well, that's okay.
On 2 slides before, another one? Yes. Say you have a equivalence class that says x minus x and 0. Now you say, well, 0 is a better interval, I'm going to take that. You're doing early pruning.
Doing what, sorry?
Early pruning, right? So if, let's say, you take all of those rewrites, and you take a small graph and you run everything greedily, all the way full space search, you end up with a humongous graph. How do you know which path to take to generate the perfect RTO? Okay, so I'm trying to separate the two. So there's one thing that's about, so firstly, let me prelude by saying the best path or the best kind of set of expressions, and it's not always one single expression, for analysis isn't necessarily the best
for RTL generation, right?
Okay.
That's the first thing I would say,
Okay.
right? But let's talk about the analysis first, right? So for the analysis, I think probably the point you're getting at is that point I made, that we do indeed identify cases where the left-hand side of the interval, the best left-hand side of the interval, comes from one expression. The best right-hand side of the interval comes from another expression in the E-class, and neither of them were the original expression that we had.
Right.
Right. How do we deal with that in the case of early pruning, as in throwing away, what you've...
Ignoring the x minus x and going through and using the 0 as the path through that node, but you might get an x minus x converted into something else that now makes it much smaller because you recognize a pattern that 0 doesn't give you.
Yeah.
Like 0 collapses an entire dimension of your analysis,
Yeah.
and you miss something that is much better down there. It's like gradient descent into a local minima rather than a global.
Yeah, so I mean, I think the... so this is a particularly trivial example, right? In the paper, there are kind of more sophisticated examples. But I think, again, going back to what I was saying, what we find is that it's not that rewrites for analysis, and indeed the optimal rewrites to fire for analysis, are not necessarily those for RTL. What we haven't done, I think, to the best of my memory, is to explore what would be a good class of rewrites for analysis, right? And I think that would be a really interesting thing to look at, yeah.
Thank you so much for the talk. I guess one of the things which can break down with E-graphs is when you have like poor heuristics during extraction. Could you talk a bit more about how you designed efficient but kind of representative heuristics for extraction to get the results you did?
Extraction. Yeah, okay, right. Yeah, so, I mean, extraction isn't something that we've spent a huge amount of time on. So the way we actually do the extraction is we build an interlinear program to do the extraction. That's what we do. Now, obviously that ILP doesn't have to be solved to optimality, okay? But that's the approach that we take. I'm aware that there's some quite recent work from a number of people, in fact, but including from my colleague Jiru Zhang at Cornell, that have looked at ways to kind of accelerate that process. Not something that we've really looked at in any depth. But you're right, it's a key problem, yeah.
Hi, thanks for the talk. Going back one slide, you had this x minus x and 0 example. So a more powerful abstract domain, like a relational abstract domain, would be able to track the equality between x and itself and therefore tell you that it's 0, and therefore be more precise. And I'm wondering how the added precision you get with the virtuous cycle between E-graphs and abstract interpretation compares to simply using a more powerful abstract domain.
Yeah. And that's essentially what I'm alluding to in my ideas for future work, right? I don't know the answer to that. I think essentially you get a kind of relational abstract domain by applying this at an E-graph level, right? But I'd like to kind of bottom out that to a more precise theoretical basis, and I don't have an answer for you. But yeah, you're right. I mean, essentially there's a balance. Use a simple abstract domain with lots of rewrites that allow you to do interesting analysis, which is kind of the way we went. You could have a much more sophisticated relational abstract domain that may not require as many rewrites to do a good quality analysis. Actually, to be honest, that's the way I thought the research would go, but we found out that it was so powerful just applying this simple analysis with the rewrites that we didn't bother to explore that route. But there's a kind of nagging question about when this doesn't work, and I'd really, really want to bottom that out.
I've got a sort of conditional question. So first, sort of a naive question. The answer might be, go read the paper, it's in there. In the examples that you've shown,
Yeah.
it was all just simple arithmetic expressions that we're optimizing without any sort of state, sequential logic, things like this, right? But what I want, is it limited actually currently to arithmetic expressions in Verilog?
Okay, so that's a good question. So certainly our focus is on Datapath. So we wanted to focus on word level operations, okay? But there are certain things that are enabled by including bit level operations in there, and we do have those in there as well. But we haven't kind of got a good answer to what's the ideal bag of rewrites to have in this context. I think, so related to your question, so the other part of your question is around sequential logic. So what we have done in a paper that extends this, so I haven't spoken about this, in a paper that extends this to low power, rewrites for low power, is to lift from operations on single words or bits to streams of words or bits. And we needed to do that in order to do power optimization because of the temporal element involved in that. And so that's one area where we have looked at sequential operations. But it's not something that we've done kind of in depth, I would say.
Okay, and then the lead-on question to that is, because this is the path I was hoping for, there's a part of guided eGraph exploration. Like what I want, my daydream is that I have not just an arithmetic data path, but I've got a pipeline of, I don't know, an audio processor. I've got different stages. I want to guide you. I want to say, hey, please don't renormalize these floats. Is one example. It'd be amazing if this sort of tool, with a little guidance, would say, hey, you shouldn't renormalize between these two stages in your pipeline over these connections. Is that something that you can do, could do?
I mean, it's not something that we do by any means. I know that in the eGraph community, there are people who are looking at those kind of questions. And the other side of that is to also look at the selection of rewrites through a machine learning lens, right? I've got a clear state space here. I've got a clear action space. How do I make use of that, right? And I think, again, there are people that are looking at that, but what we've done is literally just used the egg tool out of the box to decide what rewrites to apply when.
Yeah, hi. Thank you for the talk. I was just wondering, you had a table, the massive table where you had like a bunch of sufficiency conditions and a bunch of rewrites. But this is like only taking into account like the very accurate, perfect translation rewrites, while often you have a bunch of don't care states in reality. Is this something you've been able to like work with? Because I would expect you would be able to get a lot more efficient optimizations if you just add don't cares. Is this even possible to do efficiently?
It's an excellent question. And again, if you want to work on that, I'd love to work with you on that. It's something that I've given some thought to. Okay, let's put it that way. I mean, ultimately, the problem is that it doesn't sit very nicely with the whole idea of an equivalence relation in the first place. And that causes some difficulties. Have some thoughts about maybe how to address that, but it's something that needs a lot of work.
Yeah, that's actually a really interesting question. So maybe one more question.
Thanks for the talk. Do your eGraphs have loops in them?
Have they? Do they?
Have they got loops in them?
Yes, they potentially have loops in
so
them.
Then
yes.
How do you? Is it obvious how you like propagate this interval information through your eGraph? Does it need to be some fixed point or something, or?
Yes.
How do you? Okay.
Yes. So that's another good question. So yes. So we discussed this in this paper here. So the eGraph construction can lead to loops. The question is, what's the kind of meaning of these loops when it comes to this interpretation? And yes, it's around construction of fixed points, absolutely. Unsurprisingly, I think there's another really interesting kind of neat little bit in this. I think it's in this paper where we actually also can interpret those loops as giving rise to some operations on intervals, like interval-based calculations. So, for example, there's an algorithm for solving systems of linear equations in interval arithmetic that's called the Kravchuk algorithm. And so it turns out that you can kind of automatically derive the Kravchuk algorithm by considering what one of these loops looks like in one of these. So I think it's, again, an area that's ripe for exploration. We've kind of marginally explored it, I would say. Yeah.
Thank you.
Excellent. Yeah, I mean, plenty of questions. So some of you may know we have afterwards the compiler social. So George kindly agreed to stick around for a little bit. So if you have more questions, you may have a couple of hours, or at least a little moment to ask George. Thank you again. It was an amazing talk. Thank you so much.
Thanks, everyone.